So this is the lecture number 18B. So in part A, we looked at how the stiffness matrix, like we have this equation, right? So we have this for element, this element stiffness matrix, and we have element displacement vector is equal to element force vector, right? Some we get this, and we know that in order to get the entries of Ke, for example Kij, it has to be integrated. So you have to write 0 to Le, and then we have here dNei dxe multiplied by Ea dNej over dxe dx. So there is an integration involved because E may be changed, E may be a function of x, A can also be a function of x, N is a function of x already, right? So that means this term could be complex, and we have to find out the values. Values means correct values, yeah. So we need to have numerical integration, yeah, numerical integration. So here in this lecture video, we will look at the numerical integration, specifically a method called Gauss Quadrature. Okay. So basically, what is the idea? The idea is we have some integration. Let us say we have from a to b, and we have some function of x. We have to, this is one dimensional, yeah, and then we have to integrate. And how to do that? Well, we have to first look at the possibility, which all kinds of things accuracy we can attain. Okay. So first, so that we have some standard form of this, we can also translate this one, the I values, I is equal to 0 a to b f x dx. We can also write it as -1 to 1 and f maybe xi and d xi, something like that. Okay. Now this in order to do that, we know that if x is a, then xi is -1, and then x is b, xi is +1. So we can have like x can be expressed in some terms of xi, and this will be x equal to, in that case will be x a plus b over 2 plus xi multiplied by b minus a divided by 2, and we can check it, right? So let's say xi equal to 0, right? So what is the variation? Variation like this one. So you have varying from a to b, and here your variation will be -1 to 1. Same kind of, we should have the same kind of function both the sides, right? So we can see here, like if x this is a function fx, right? So this is fx, this is f xi. Okay. So you put xi equal to 0 here, and hence you have a plus b over 2, that's the middle of this one. So 0 is corresponding to a plus b over 2. Put xi equal to 1, so you have a plus b minus a divided by 2. So you will have 2b over 2, hence b, so b corresponds to 1. Then you have xi equal to minus 1, so you have a plus b minus b plus a, so b minus b, so 2a divided by 2, so a, right. So you have a value here. Yeah. So they correspond to each other. So if you have this standard format, then it becomes very easy, because you can then make some kind of table and all. Yeah. So hence it's good. Yeah. Also later on we will see that we can actually also have some like kind of elements where very like curved faces or the boundaries of one element can be dealt with, easily dealt with, like irregular shape, something. Let us say if you don't have rectangle, square, instead of that you have this kind of element, then we can have isoparametric element, you know, in terms of this kind of things, where any irregular shape where you have x and y can be you know, reshaped as you have xi1 and xi2, where we are mapping from irregular shape to a square shape. So all those things we will do we will do more of like this one later on when we are studying the 2D elements. But apart from that, you also have the advantage of actually the integration and all, where you can have a table, a standard table for this, and from there you can extend to any kind of expression here. Yeah. So hence we will just find out how to integrate this kind of expression. Automatically you can do this transformation and we can find out what. Yeah. Okay. Now here if you have to find out this kind of equation, then what do you have? So from here, how to transfer from here to here, so that we can once you have let us say you have to find out the integration of this, we will, and you know you have a table for this kind of integration, then you have to first convert from here to here, and you can do it very nicely. You have this, so hence you can say dx will be equal to b minus a over 2 times d xi. Yeah. Okay, and then you can put from dx you can put value here, and a of x you have to convert into xi. So you have I equal to a to b fx dx equal to minus 1 to 1, and then you have the fx here, so this becomes f xi. Okay, you have to convert fx into f xi, and then you simply put a x in terms x equal to a plus b over 2 plus b minus 1 divided by 2 multiplies by xi to fx form, then you will automatically get this one. Then dx will be equal to d xi multiplied this one, right, b minus e. So this b minus a over 2, and then you get d xi. Okay. So basically whatever we wrote here, it's actually not entirely correct. It's not 0. We need some what is called Jacobian here, right? So there is some constant here, let's call j here, right? So j for Jacobian. So there has to be some constant which should come here. Yeah. So and that constant is nothing but b minus a over 2. So you say j equal to b minus a over 2. Yeah. Okay. So so you have this expression, and which is equal to b minus a, nothing but the length of the element, right? So you can write le over le divided by 2, right? And then you have minus 1 to 1 f xi f xi. Okay, fine. Now the next is what is the how to calculate this one. Okay, so how to compute minus 1 to 1 f xi d xi. Okay, so f xi we can have a general expression, right? We can say this is equal to alpha naught plus alpha 1 times xi plus alpha 2 times xi square, so on till alpha n times xi n. Okay, so the order of the polynomial, okay, in this case is equal to n, right? So this is the n is the order of polynomial, yeah, okay, or you can say alpha p times p as well. Okay, so let's use order of the polynomial p basically. So y in your book also I think is written like this one, so you will not be confused. So like this. Okay, okay. Now if that is the case, then this p is the order of polynomial is p, hence number of unknowns will be equal to p plus 1, right? So you will have alpha naught, alpha 1. So number of coefficients equal to p plus 1, that is what, alpha naught, alpha 1, alpha 2 to alpha p, yeah. Okay, now if you integrate it, then what happens? Let's integrate it. So 0 not 0 to minus 1 I equal to minus 1 to 1 f xi is equal to, we have minus 1 to 1 f xi is alpha naught plus alpha 1 xi plus alpha 2 xi plus alpha p xi p d xi, yeah, okay, will be equal to, we will see alpha naught. Okay, this also we can write like this one also, yeah. So this is equal to minus 1 to 1, and then you have like this 1 xi square, right, then xi p, and then you have alpha naught, alpha 1, alpha 2 to alpha p d xi, yeah, okay. And which is what you get? You get something like this 1. So now you have to get the values, right? So you will get like this one. So you have xi from 1 to minus 1, xi square over 2, 1 to minus 1, xi 3 over 3, right, 1 to minus 1, and so on, right? You will get like this one, and then you will have the same matrix, right? So let's call it this alpha vector, okay? So this alpha vector is nothing but the whole vector from here to here is the alpha vector. Okay, so what is the value of this? What is the value? The value will be equal to, if you see here, 1 minus 1, so becomes 2. So this will be 2. Here a square, so 1 square minus 1 square, so will be 0. What is the value here? Will be 1/3 minus minus 1/3, so 2/3, and so on. You will get, yeah, multiplied by alpha vector, where alpha vector is nothing but this thing, alpha naught, alpha 1, like this one. Okay, so we know that the exact solution will be something like this one. Yeah, so you have depending on the number of the order of the polynomial, you know how many alphas will be there. Yeah, and if you once the number of alpha decided, here also the same thing will be decided, and you can find out, right. So this calculates the exact solution. Now the Gauss quadrature, okay, so it gives a formula basically, and it tells that I can be written as summation of wi, yeah, wi times f xi I, okay, where I equal to 1 to number of points. Okay, so what is the meaning of that? The meaning of this is like this. So let us say you have xi here and f xi here, and you have like this one. It tells that what you have to do is you have to identify some Gauss points. It's called Gauss points. Okay, so you can find out some Gauss points. So these are the Gauss points here, here, here. So let's call this is xi 1, xi 2, xi 3, and you know the value here. This will be from here to here, it will be f xi 1, right. Similarly, this will be f xi 3, like this. So this is what the will look like. Yeah. Well, only thing now is, so what will the value of w, right? So what is the value of w, and what is the value of xi I? So accordingly we have to find out. Okay, and how you can find out? We can find out for exact value. So let us say the function we have already, we know, right? The function is equal to what we have. We have 1 xi square and so on to xi p, and then you have alpha, right? So you have alpha vector, where alpha vector is nothing but we have alpha naught, alpha 1, alpha 2 to alpha p. So we have that. Yeah. Okay. If that is the case, then we know that this tells us that f xi 1 will be equal to 1 xi 1, xi 1 square and so on, xi 1 p times alpha. And similarly for 1, 2, 3, 4 and all, right. So we have xi 2 here, so you just have 2, 2, 2 here. If you have xi 3, you have 3, 3, 3 here. Yeah, so we can find out like that. Okay, now we have to match, right. So whatever this is the integration, this integration and this integration, both have to match. Okay, so this is also integration, the same value we want to calculate. The idea is we have to match the values, we have to find out the w's so that we get the exact integration, exact value. Yeah. So if this I goes from 1 to np, so we can write this as how will you write? So this will be we have f xi which is written like this one, then we have w, so we have to write w1 times this. So let's write like that. So according to the Gauss quadrature, we are going to write as the summation I equal to 1 to number of Gauss point and GP, and then we have wi and then have f xi I. Okay, this is how you are writing, right? Okay, so basically this will be you can also write this will be something like this. We will have W1, W2, 2, how number of Gauss points. So we will have till W n GP, right? And then we will have the value of f. So then we will have like something like this one, f xi 1, f xi 2, and so on till f xi the ngp. Okay. However, each of these function f xi is given like this, right? Is given like this one. So can we write somehow in the matrix form? So basically here this we can write as a matrix. So this f xi 1 is written like this one. So we can write this and alpha. So basically how you can write? We can write the same thing as this is equal to W1, W2, or let's call it a W vector, right? So say the big W vector. Yeah, this is okay. This is not the same W that we were talking earlier. This is not a way that weight. This is weight for the integration. This is different weight. Okay, so this is not W. That's why I did not write like that. Okay, so this is for integration purpose only, nothing to do with the weak function. Okay, so this W, this W is nothing but actually we are talking about this one, and then we can have like this equal to, and what have 1, then we have xi 1, xi 2 to xi p, similarly 1, xi 2, sorry, this should not be like that, it's wrong. So we will have xi 1 square to xi p, sorry, not p, xi 1 only, p 1, xi 2 square, xi 2p, and so on. Then you have 1, and then xi we have ngp, so ngp, xi ngp square, and so on, xi ngp to power p, yeah, like this one, and then you will have alpha. Yeah, so why we do this? Alpha has alpha naught, alpha 1, alpha 2, and alpha naught multiplies to 1, alpha 1 multiplies to like this one, and hence we are getting f xi 1. So you get f xi 1, this multiplied by this, f xi 1, this multiplied by this, f xi 2, and so on, right? So this I, from according to the Gauss quadrature, we get this one, but if you integrate it directly from the function, we get this value. Okay, so meaning what? Yeah, we have this times alpha is equal to this times alpha. That's what we are getting. Okay, so then what do we get? Then basically we are getting like this. Say if you compare this one, right? So you can, if you compare both of them, let's say this is equation number 2, okay, and the first one, this one was equation number 1. Yeah, so from 1 and 2, both should be the same value. If you want both to be exactly the same, from 1 and 2, 1 and 2, that is Gauss Quadrature formula gives the exact integration, then 1 equal to 2, and that gives us like this. So in that case we have 2, 0, 2 over 3, so on, multiplied by alpha is equal to what do we have? We have first a weight, okay, we have weight, and then we have the zeta one, right, this one, this is the matrix, okay. So we have the weight, and then let us say we call it a matrix M, and then we have alpha also, okay. Okay, and since alpha is not equal to 0, right, so alpha, since alpha entries are not zeros, okay, so what do we have? We have simply W, say W times M is equal to this 2, 0, 2 over 3, and so on. Or you can say, you can take transpose and say, then you get M transpose, and then W transpose will be equal to simply 2, 0, 2 over 3, and so on. Yeah. Okay, so this gives you relationship. This tells you how to get weight values like W1, W2, W3. Yeah, and M has zeta 1, zeta 2, zeta 3 values. Yeah, xi, sorry, not zeta but xi. You have xi 1, xi 2, xi 3, and all in this one. This has W1, W2, W3 in this one. Hence, this gives you some idea. So this is has xi 1, xi 2, etc., and this has W1, W2, etc. So this gives you idea in order to calculate the exact value of xi 1 and xi 2 and W1, W2, how to calculate that. Okay. Now we should have also idea that how do we know that the integration will be exact or not, and that is depends on the basically how many terms are there in the polynomial, right. So we have see, if f zeta, so we have f not zeta, f xi is equal to, we say this is alpha naught plus alpha 1 xi plus alpha 2 xi square 2 alpha and p xi p. So unknowns here are, how many terms are there? Unknowns here is equal to p plus 1, and hence integration of f xi d xi minus 1 to 1 will have p plus 1 unknowns. Right? So the function can have any value of alpha 0, alpha 2, and alpha 1. You know, so number of unknowns here is p plus 1, and we are, and Gauss quadrature, if you see, if the np, if n number of Gauss points, if there is the number of Gauss points are 1, then your the integration is w. Okay, so what I mean to say is, if I, right, so if I, and Gauss quadrature, if you see, if the np, if n number of Gauss points are 1, then your the integration is w. Okay, so what I mean to say is, if I, right, so what I mean to say is, if I, so what I mean to say is, if n number of Gauss points are 1, then your the integration is w. Okay, so what I mean to say is, if I, Okay. If I equal to summation wi and where I equal to 1 to NGP Wi times f xi I. So, what it tells you? It tells you that for every number of gas points there are two unknowns. One is Wi, second is xi2, right? So, it tells you there are 2 times NGP unknowns, meaning that if we want to use that equation, right, so then we have to accordingly select number of Gauss points, right. So, if you are doing this integration analytically, then you know that we have p plus 1 coefficient. If you are doing the integration using the Gauss quadrature formula, then you know that there are 2 times NGP variables. So that we may match them this and this, then we have to have like so that Gauss quadrature gives exact integration. It's possible only when we have this number of polynomial, this one has to be less than this value, right. Okay. So, if your number of Gauss points more than required, this fine, right. So, meaning that this is what it tells you, that p plus 1 has to be less than 2 NGP. Yeah, this is what tells you. You have more than the points required, then it will calculate the integration. So basically the p value you can find out. If p is the order of the polynomial, p is less than 2 NGP minus 1, then integration is exact. If this condition is not matching, then the integration may not be exact one. There may be some error. Okay. Okay. So we can see some example. So let us say line. Yeah. So p equal to, see, like a p equal to 1. P equal to 1 means f xi equal to alpha naught plus alpha 1 x. So how many points are needed in that case? If you this tells you that the p equal to 1, so put it here, p equal to 1 here. So from this formula it tells you that 1 less than 2 NGP minus 1, or it tells you that simply NGP should be greater than 1, right. So 1 and 1 2, and that makes as long as NGP is more than 1, it will fine. Means NGP equal to 1 is also fine. It tells you that just only one point can exactly integrate. And how to find out? So let's go to this earlier equation, and we know that in this case we have p equal to 1 value, and hence we have m times w equal to 2, right? So you have W1, W2. Here we have transpose of M, where M is like this one. So we have 1 zeta 1 square, zeta 1 square, and so like this one. We have P value equal to 1, so we will have 1 zeta 1, right? Okay, and then number of Gauss point is only 1, so we have just this value, right? So here M, the M matrix, so look at this, we have NGP equal to 1, number of Gauss points on 1. So this is, we are interested in only this one only, and here we are saying P equal to 1 only. So we have this one, and this is the M matrix. The transpose of that will be 1 xi 1. So we have 1 xi 1. Okay, so we have M matrix for us will be 1 xi 1, transpose of that. Okay, so we have that. Okay, and then we have that M matrix, then W transpose. Yeah, so the W transpose will have let's say what is W. So we wrote like this. So this is the W. Okay, so this is W. So W transpose, that means we have W1, W2 like this, but we have W1, but we have only one point, NGP is only one point, hence we have just W only, there is nothing else. Okay, so we have just W1. So we will, accordingly we can write this is W1 is equal to and what is here is equal to 2 is equal to 2 and equal to 0, is equal to 2 and 0. Yeah. So equal to 2 and 0. Okay, so we got this formula, yeah, and what we see, you see here we have these two equations, and we have two equations. So it gives you W1 is equal to 2 and xi 1 and W1 equal to 0, right? So this gives you two things. This gives you W1 equal to 2 and xi 1 is equal to 0. Okay, that means if you want to integrate a line, we can exactly integrate like this. Now let us say you can see the example. For this example you can say, like, let us say you have a line like this one. Say you have xi equal to, sorry, f xi f xi equal to 2 xi plus 3, let us say. This you have to integrate, and then how to integrate? Integrate from xi equal to 1 minus 1 to 1. Let us say you have to do it. So what it tells you, that if you have to integrate like this one, this is minus 1, let us say this is 1, and this tells you that you just have to do W1 times the integration. I will be equal to W1 times f xi 1, that is it. Where W1 is equal to, we have calculated W1 equal to 2 and xi equal to 0. So equal to 2 into f at 0 is equal to 2 times xi equal to 0, put it here, so becomes 3, so we get 3 is equal to 6 is the answer. Okay, and you can integrate also, you can find out if you say I, okay, check whether it's correct or not. You can say I equal to 2 xi plus 3 d xi minus 1 to 1 will be equal to 2 xi square over 2 plus 3 xi, right, 1 minus 1, and what you see here is this is xi square, hence this value will be 0, and what you have xi here, so 1 minus 2, so 3 times 2 is 6, so it will be 6 value, right. So this matching basically, yeah. So they are matching. Similarly, you can find out for NGP equal to 2, right. So for say you have a quadratic equation now, right. How to, not how to, but what if quadratic equation. Quadratic f xi, yeah. Then what do you have? You have f xi will be something like this: alpha naught plus alpha 1 xi plus alpha 2 xi square, right. Okay, if that is the case, then you have p equal to 2, right? And hence you know the p plus 1 has to be less than or equal to ngp, you can check, and then you have 2 plus 1 is 2, right. 2 plus 1 has to be less than or equal to 2 ngp, and hence you will have ngp can't be fractional, ngp is either 1 or 2 or 3. So what you see here, ngp has to be equal to 2. Why? Because if it's 1, if ngp equal to 1, then it becomes 2 greater than 3, not possible. Now if ngp equal to 2, this is 4 less than or equal to 3, so this, so ngp will be 2. So you will need 2 points to exactly calculate this one. Similarly, if f xi is cubic, then what happens? Then p equal to 3, and then you have 3 plus 1 less than or equal to 2 ngp, and hence it tells that 2 get less than ngp. So as long as this tells that this had to be 1.5 ngp, and hence this tells ngp has to be 2. Even for cubic also, you just need 2 ngp point, that's it. So cubic functions can be calculated with can be integrated just with 2 points, right. Okay, so we can say in case of cubic can be exactly by 2 points. So we know that ngp we have to take equal to 2, and p you have to take as 3, and this is going to calculate exactly, yeah. So let's go to that equation, and what do we find? So here, okay, so m times w equal to this, so equation, okay, here m times w, so w we have p equal to 3, right. So p equal to 3, so we will have 1 xi square and xi to power cube, right. So we have 1 2 3 4, and then ngp equal to 2, so we have 2 of them, so we have like this, but we have to transpose this one. So you have 1 xi 1 square, and so on like that. So this is what the matrix M is. Okay, so let's write that. So our matrix becomes like this: 1, then xi 1 square, xi 1 cube, right, and similarly you have 1 xi 2 square xi 2 cube. This we get m, okay, times weight. Now there are only NGB equal to 2, and hence we will have only 2 weights. Yeah, so we have W1 and W2 only. Yeah, so we have W1, W2 times weight. Okay, so we have m okay, so m transpose and then W, so we have W1 W2 is equal to, we will have this one. Yeah, so here we have to write 2 0, so depending on how many terms will be there, so it will be 2 then 0 2 over 3, and we can there will be 0 here as well. Why 0 here as well? So you can see that there will be a square term there. Yeah, so where did we calculate that? So go back. Here, okay. So if you see here, if 1 xi square, if xi cube is here, let's add xi cube. Okay, so we need it, this one. So this value will be actually, if you see, this becomes xi 4 over 4 and 1 to minus 1, and since this is even number, hence this will be value will be 0, so we will have 0 value. Yeah, so we will have 0 value. Since we have to take four of them, hence we have taken accordingly write as like this. Okay, has to be 4 number this side, because we have 4 by 2, this is 2, this is 2 by 1, so it has to be 4 by 1. 4 by 1 is 2 0, then 2 over 3 0, like this. So this is the equation that we have to solve in order to get it. Okay, so we have 4 unknowns, which xi 1 xi 2, and then W1 W2, and we have to find out with the 4 equations. Hence you will get, first is W1 plus W2 equal to 1, equal to 2. Okay, so let's assume W1, in fact automatically it will be somewhere, it will be automatically it will be W1 equal to W2 only. So let's say W1 equal to W2, we want a weightage. Yeah, so just to help solve it, we can check whether this condition is being satisfied or not, but this will help us to solve it. Okay, now next is xi1 and xi2, right? So this tells you xi1 times W1 plus xi2 times W2 equal to 0. Okay, so if say W1 equal to W1 equal to W2 equal to, let's say, W, so this becomes W, and then xi1 minus plus xi2 equal to 0, right? And this tells us that xi1 plus xi2 equal to 0. Okay, next thing is W1 you can see from here also that this one, W1 multiplied by xi1 square, so last term is W times xi1 square plus xi2 square is equal to 0. This actually tells you simply that xi1 is equal to minus xi2, right? And this is basically we can also see here, because they are opposite of sorry, this had to be cube. Yeah, so they are opposite each other, hence it will cancel out. Yeah, so this basically is true. So xi1 equal to xi2. Only thing we don't xi1 equal to minus xi2. Only thing we don't know how much the value is. So that we will get from this value. So xi1 square w. So we get so w. Okay. So here w1 plus w2 equal to 2. Assume w1 equal to w2 equal to, it becomes equal to 1 only, right? So w equal to 1 only. To 1, because w1 plus w2 equal to 2, both same, so w1 equal to w2 will be equal to 1 only. So we get the weight already. So this equation, this multiplied by this, has to be equal to 2 over 3, and hence you can, basically what value you get. So you get w multiplied by xi1 square plus xi2 square. Let's call it xi naught. Okay, so xi1 square plus xi2 square equal to 2 over 3 is equal to w is equal to 1. So we write 1 multiplied by xi1 equal to minus xi2 equal to this. So what you get is xi naught square plus xi naught square. So 2 xi naught square, and hence this tells you xi naught square is equal to 1/3, and hence xi naught equal to 1 over root 3, and this tells you that w1 over w2 equal to 1, and xi1 xi2 is equal to plus minus 1 over root 3. Yeah. So you found out basically. So in the table, actually the Gauss quadrature, there is a table. Please refer to your book, chapter 4. Towards the end, there is a table given. This tells you how to exactly what are the weightage, what is the value of the weightage. This is w1, w2. You find out for the, if you want to integrate a cubic function, then you can just integrate by saying w1 times f xi1 plus w2 times f xi2, where w1 is equal to 1, w2 equal to 1, and xi1, xi2 are plus minus 1 over root 3, and it is going to solve the problem. Okay. Okay, so that is all for today.